Assalamualaikum warahmatullahi wabarakatuh and very good morning everyone. So today we continue our lesson on Digital Electronics Chapter 8, Counters and Shift Registers. So for the first part of the topic, it is related to the counters. So at the end of this topic, you are expected to know what are the various type of counters and how to design the counter circuit inside the digital electronic circuit. So without further ado, let's continue. So the first part of this topic, I will show you the introductions of counters. So what is actually counters? So counter is a group of flip-flops that are connected together to perform counting operations. So basically, counter is grouping parts of the flip-flop. So it means that you have a few flip-flops inside one counters. So as usual in our daily life, we are used to count things. For example, we wanted to count the number of machines, or we wanted to count the number of tests that we have. 1, 2, 3, 4, and 5. But what about in digital electronics? So in digital electronics, the counting works is done by the counter. Okay? So the number of flip-flops used and the way which they are connected will determine the number of state and also the specific sequence of states the counter goes through during each complete cycles. So in counters, if you wanted to vary your number of states and also the states of the counter, whether it is counting up or counting down, you need to connect your flip-flop in variation. Okay, so in order for you to get what you call the various output of your counter, you need to connect your flip-flops in different connections. Okay, so the example of one of the counters is a 3-bit binary counter. So this is the logic symbol of the 3-bit binary counter. So for this 3-bit binary counter, you see here, the clock is negative age triggered. So it means that the output will change at the falling edge of the clock. So you see here, the second input, it also have the clear input, which is usually used to clear up the count. Okay, so if the CLR is activated, the count will reset. Okay, and then we have three outputs, which is Q2, Q1, and Q0. And usually Q2 is used for MSB and Q0 is used for LSB. Okay, so for counter, if we set the CLR to 0, so this one is the active low activated. So if CLR is equals to 0, the output of the counter will become 0. So it means that the output has been cleared. Okay, but if CLR is equals to 1, so if the CLR pin is equals to 1, so it means that the counting situation will be happen, where if the counter detect the negative edge, which is the falling edge of the flip-flop, the counting will start, where the output will add to 0, 0, 1. Okay, so in this 3-bit binary counter logic symbol, so this counter, it is used to count the binary number. So each stage will add the number of 0, 0, 1. Okay, else if if the counter doesn't detect any falling edge, so the output will remains. Okay, so it will maintain the previous value. Alright, thus the output waveform for Q2, Q1, and Q0 are, so this is the example of the timing diagram, the general timing diagram used for the 3 bits binary counter. So from the timing diagram, we can also get the state diagram. So first, the counting start from 0, 0, 0, and then when it detect the the falling edge, it starts counting. Okay, because the clear has been set to 1. Okay, so when the clear has been set to 1 and the falling edge is detected, the counter will start counting. Okay, so from 0, 0, 0, it will become 0, 0, 1. and then on the next falling edge it will become 0 1 0. Next falling edge it will become 0 1 1. Next falling edge it will become 1 0 0, and then at the next falling edge it will become 1 0 1, and then 1 1 0, and finally 1 1 1. Okay, so this what we call the value of 0 0 0 0 0 1 and so on is called a state. Okay, and then the what we call the transition from, for example, 1 0 1 to 1 1 0 is called the sequence. Okay, so this diagram, this what we call full diagram, is called a sequence diagram inside the counters. Okay, because the counter is used to make a count of something, so it must have a specific sequence. Okay, so next, the counters are classified into two broad categories according to the way they are clocked. So those categories are, so the first one is asynchronous counter. So counter can be categorized as two different types based on the way they are clocked. Okay, so the first one is the asynchronous counter. So what is actually asynchronous counter? So asynchronous counter is also known as ripple counter, and the first flip-flop is clocked by the external clock, and each of the successive flip-flop is clocked by the output of the preceding flip-flop. So for asynchronous counters, you see here, this is the clock signal. Okay, this is the external clock signal, and the external clock signal is only connected to the first flip-flop only, and then the second, third and fourth flip-flop will be connected to the output of the previous flip-flop. So for example, this is the second flip-flop, so the input clock at the second flip-flop will be connected to the output of the previous flip-flop. Okay, so the external clock signal is only connected to the first flip-flop only. Okay, so it will continue until it reach at the final flip-flop. Okay, so the final flip-flop also accept input clock from the output signal from the previous flip-flop. Okay, so next is synchronous counter. So for the synchronous counter, the clock input is connected to all the flip-flops so that they are clocked simultaneously. So for synchronous counter, the external clock signal, so this is the external clock signal, is directly connected to all flip-flops inside the counter. Okay, so it doesn't need to connect to the output of the flip-flop. Okay, so the external clock signal will be directly connected to each flip-flop inside the synchronous counter. So that is the difference between asynchronous and synchronous counter. Okay, okay, next is the categorization of counters. So counter can be categorized as several categories, such as the clock trigger. So for the clock trigger, we have positive edge, which is triggered only at the rising edge. And then we have negative edge, which is the output will count only at the falling edge. Okay, so for clock trigger, if the counter is positive edge, the count will be conducted only at the rising edge, and for negative edge, the count will be counted on the falling edge. Okay, the next categories of counters is the count type. Okay, so for the what I call the number types, we have the binary counter, which is, for example, 0 0, we count it into 0 1, and the next number will become 1 0. So this is the binary number count. And also we have the decade. So the decade counter is about the what they call number of base 10, which is 0 to 1, 1 to 2, and 2 to 3, and so on. Okay, and the last type of category is the count direction. Either it is up, so 0 1 2 3, either it is down, which is 3210, either it is up or down. So it can do both 0123 or 3210. So from here you can see that the counters can be categorized as three categories, which are clock trigger, count, and also count direction. So each category of counters has different connection of flip-flop inside the counter. So later on you will see how we wanted to design the positive edge counter, negative edge counter, binary, decade, and also the up and down counters. Okay. Next, I will show you the functions of counters. So, what are actually the function of counters in digital circuit? So the first function of counter is to count the number of time that the certain event take place. For example, if you wanted to know what is the number of events that occurs, for example, if you wanted to switch on or switch off LEDs, you can count how many times you want the LED to be switched on or off by using counters. Next is to control a fixed sequence of actions in digital system. For example, if you want to design a system where you have a total of 3 different LED, and then you want the LED to have a fixed sequence. So in order to do that, you need to use a counter. Okay, the third one is to generate the timing signals. So from the previous lesson, you already know how to interpret and how to generate the timing signal. But actually, the timing signal is generated based on the counter. And lastly, to generate clock of different frequencies. So for clock in digital electronics, each clock has its different frequencies. So to design the clock with different frequencies, you need a counter. Okay? So next, I will proceed to the asynchronous counter. So what is actually asynchronous counter? So asynchronous counter is one in which the flip-flops within the counter do not change state at exactly the same time because they do not have a common clock pulse. So from the previous slide, I already shown you the circuit of the asynchronous counter, where the external clock is only connected to the first flip-flop. So the clock input is always connected only at the LSB of flip-flop. So if you see an asynchronous counter, if you see the external clock is connected to that specific flip-flop, so it means that that specific flip-flop is the LSB part of the counter. Okay? So the clock for the next flip-flop comes from the output of the previous flip-flop. So what about the input clock at other flip-flops? So the input clock at other types of flip-flops comes from the output of the previous flip-flop. Okay? So asynchronous counter is also known as a ripple counter, which is the message or signal passing. So this is the circuit of the asynchronous counter. So you see here, the external clock is directly connected to the first flip-flop. So from here, it means that FF0 is the LSB. Okay? So the output of the LSB part of the counter will be connected to the next flip-flop, and it will be connected to the clock input. Okay, and it will produce a total of 2 bits of output. So this is the 2-bit counter. Okay. Okay, so for a synchronous counter, the flip-flop 0 changes state at the positive edge of each clock pulse. So for flip-flop 0, you see here, the input clock is positive edge triggered because it doesn't have any bubble at the clock input. But flip-flop 1 changes only when triggered by the positive edge of the Q bar output of flip-flop 0. So as you see here, the flip-flop 1, the input clock is directly connected to the output Q0 bar from flip-flop 0. So flip-flop 1 will only changes when it is being triggered by the positive edge of the Q0 bar of flip-flop 0. So because of the inherent propagation delay through a flip-flop, the transition of the input clock pulse and a transition of the Q output of flip-flop 0 can never occur at exactly on the same time. So in our previous lesson, I already explained to you the flip-flop suffers from the propagation delay, where it will have some delay when we exert an input and the output will take some time to respond. Okay? So therefore, the flip-flop cannot be triggered simultaneously. So it is producing a synchronous operation. Okay? Because the clock is only triggered at the flip-flop 0. Okay? So the transition of each output will not being occurred at the same time because of the propagation delay. Okay? For example, if we give the positive edge trigger of the clock for the flip-flop 0, it will take some time for the output Q0 and Q0 bar will be response. But after the output has some changes, if the output of Q0 bar has the positive edge triggered, which is from 0 to 1, so it will then trigger the flip-flop 1. Okay, so the trigger situation will not occur at the same time, and because of that, it is called asynchronous. So this is the example of the 2-bit asynchronous binary counter. Okay, so the previous circuit shows the example of the 2-bit asynchronous binary counter because it has 2 flip-flop. Okay, so the input JK of each flip-flop is tied up together. Okay, so we combine the input JK for each flip-flop inside the counter. So therefore, J equals to K equals to 1 will be set to high. So in the other words, the JK flip-flop function in a toggle mode. Okay, so it means that in binary counter, we set the JK flip-flop, each JK flip-flop to input of 1 because we want the output to be toggle. So if the previous output is 0, the next output will become 1. And if the previous output is 1, the next output will become 0. Okay? So every clock pulse, the Q will be complemented. Okay? So the output will be changes at every clock pulse when it detects the rising edge because it is positive edge trigger flip-flop. So every positive edge of the clock, it will toggle Q0 for flip-flop 0. And for flip-flop 1, the clock depends on Q0 bar. And the output Q1 will only toggle on the positive edge of Q0 bar. So if Q0 bar changes from 0 to 1, then it detects a rising edge. And then it will change the output of flip-flop 1. So the flip-flop 1 will be toggle. So the output of the circuit counter is read as Q1 and Q0. So in counter, for this one we have 2-bit asynchronous binary counter. So the external clock is directly connected to the flip-flop 0. So flip-flop 0 is the LSB part of the counter. And therefore flip-flop 1 is the MSB part of the counter. So the output from FF1, which is Q1, will become the MSB part of the counter, and output Q0, which is the LSB part of the counter, will become the LSB part. Okay, so it read as Q1 and Q0. Okay, so for example, if the previous value of flip-flop 0 is 1 and 0, and the previous value of flip-flop 1 is Q1 equals to 0 and Q1 bar is equals to 1, okay, the counter will read as 0, 1 because Q1 is the MSB and Q0 is the LSB. Okay, so right now your counter state is at 0, 1. And then when we exert the positive edge trigger clock to the flip-flop 1, so the output of the flip-flop 0 will toggle. So the output of 1 will become 0, and the output of 0 will become 1. And then you see here, the transition from 0 to 1 will produce the, the positive edge triggered, because the output rising from 0 to 1. So the flip-flop 1 will recognize the rising edge, and then it will toggle the output of the flip-flop 1. So 0 will be converted into 1, and 1 will become 0. So the next counter will become 1, 0. Okay, so you see here, it means that the binary counter is counting, because the sequence of binary number is 0, 0, 0, 1, 1, 0, and also 1, 1. Okay, so it means that this connection is correct and the counter is working correctly. Okay, so the timing diagram for 2-bit asynchronous binary counter is given as, so you see here, the 2-bit asynchronous binary counter, it has a clock signal, and if you wanted to know how the 2-bit asynchronous binary counter working, you need to observe 3 different outputs, which are Q0 bar and Q0 and also Q1. So Q0 is the LSB part of the counter, and Q1 is the MSB part of the counter. Okay, so this is the binary state sequence for the counter. So you see here, it has a total of 1, 2, 3, and 4. 4 different states, and the first one is actually the initial state only. Okay, so as usual, if we wanted to count something, we must start from 0, right? So for the binary state sequence, so the initial state of the counter is 0, where Q1 is 0 and Q0 is 0. Okay, so at the first rising edge of the clock, you see here, the Q0 bar will be changed to 0. Okay, and the Q0 will be changed to 1, because when the active high asynchronous binary counter is detecting a rising edge, the output of Q0 will toggle. So therefore, because the previous output of Q0 is 0, so the next output of Q0 is 1 when it detects the rising edge at the clock. Okay, so you see here, the output Q1 doesn't change, because the output that comes from the Q0 bar is falling. Okay, as the the asynchronous binary counter is positive edge triggered, so the Q1 output will only toggle if the output signal of Q0 bar is at rising edge. Okay, so next we goes to the next stage of the clock. Okay, so the next stage of the clock is the rising edge of the second cycle. Okay, so when the clock is at the rising edge of the next cycle, so because the previous Q0 is 0, so it will toggle to 1. Okay, so you see here, both pulses are rising. So it means that both output of Q0 and Q1 are changing. So the Q0 will change from 1 to 0, and Q1 will change from 0 to 1. So it means that the previous, this is the initial state where the counter is 0, 0, and the previous state where the counter start counting and then it changed to 0, 1, and then this is the current situation where the counter is becoming 1, 0. So when we proceed to the next cycle of the clock, okay, you see here, at the rising edge of the clock, the Q0 will change. So it will toggle from 0 to 1. But you see here, at the signals of Q0 bar, there is the falling edge detected. So if the falling edge detected for Q0 bar, so the output Q1 doesn't change. Okay, So you see here, the counter will become 1 1. So right now the counter has been finished counting because it starts from 0 0, count into 0 1, and then 1 0, and then it becoming 1 1. So what happened at the final stage of the counting? So at the final stage of the counting, which is the next clock pulse, so when it detects the rising edge of the next clock pulse, you see here, the output Q0 bar will toggle from 0 to 1. So it means that both input that will be given to the each flip-flop will rising. Therefore, the output of Q will change, the output of Q0 will change from 1 to 0, and the output of Q1 will change also to 0. Okay? So it means that at the fourth, what they call state sequence, the 2-bit asynchronous binary counter will reset back. Okay? So as you see here, for 2-bit asynchronous binary counter, the counting will take place at each clock cycle. As you see here, in the first clock cycle, the counter will be count from 0 0 to 0 1. And at the second clock cycle, the counter will count from 0 1 to 1 0. And at the third clock cycle, the counter will count from 1 0 to 1 1. And at the fourth clock cycle, the counter will reset back from 1 1 to 0 0. Okay. So the 2-bit ripple counter has 4 different states, each one corresponding to a count value. Okay. So it has 4 different states, 1, 2, 3, and 4. Okay. So a counter with n flip-flops can have a total of 2 to the power of n states. So because of this 2-bit asynchronous binary counter only have 2 flip-flops, so it will only have 2 to the power of 2 states, which is equals to 4. Okay. So next, we'll proceed to the 3-bit asynchronous binary counter. So how to design a 3-bit asynchronous binary counter? Okay, so the circuit connection for the 3-bit asynchronous binary counter is just the same as 2-bit asynchronous counter. Okay, so this is the circuit of 2-bit asynchronous counter. But for a 3-bit counter, you can just add another flip-flop. So from the 2 bits binary counter, you can just add another flip-flop where the J and K input will be directly connected to the input high, and the clock input of the third flip-flop will be connected to the Q bar output of the second flip-flop. Okay. So the timing diagram for 3-bit asynchronous binary counter is given as, so you see here, we have a total of 3 outputs. Okay. So for the 3-bit counter, we have Q0, Q1, and Q2, where Q0 is the LSB and Q2 is the MSB. So the 3-bit asynchronous binary counter is working the same as the 2-bit binary counter, but with an additional bit. Okay, so this time you can count a total of 7 different count. Okay, so the counting changes at every positive edge of the clock, which is similar to the previous example, and the counting sequence is 0 1 2 3 4 5 6 and 7, and then it will recycle back to a count of 0. So you see here in this timing diagram, for each clock pulse, the output will change because it is positive edge triggered. Okay, so for the first, what I call the initial state of the counter, it is 0 0 0, and when it detects the positive edge of each clock, it will become 0 0 1 0 1 0, and then at the third, what you call positive edge, it will become 0 1 1, and then 1 0 0 1 0 1 1 1 0 1 1 1, and then after it reach the value of 1 1 1 at the 7th clock pulse, at the next clock pulse it will recycle back to 0. Okay, so it will become 0, 0, 0 back. Okay, so this is the binary state sequence for the counter, where it has the initial state of 0, 0, 0, and then it will count from 0 to 1, 2, 3, 4, 5, 6, and 7, and at the 8th pulse it will recycle back to the count of 0. So for 3-bit asynchronous binary counter, it has a total of 8 states, okay? Because 2 to the power of 3, 3 is the number of flip-flops, so 2 to the power of 3 will become 8. So we have 8 states, okay? Because the initial state doesn't count it. So next is the 4-bit asynchronous binary counter. So can you guess how we can design the 4-bit asynchronous binary counter? So the circuit connection is just the same as 3-bit asynchronous counter, but for a 4-bit counter, you can just add another flip-flop. So this is the circuit of the active low age triggered, okay, 3-bit asynchronous binary counter. But for 4-bit asynchronous, we can just add what we call the next flip-flop, okay, the 4th flip-flop. So you see here, the clock has a bubble here, so it is negative age triggered. So for negative age triggered flip-flop, if you want your counter to count up, you must connect the output of Q to the next active low clock input, okay? So if you have active high clock input, you will connect to Q bar if you want your counter to be count up. So later on I will show you what are the differences between count up and count down counter, and also the positive age and negative age triggered counters. So in the example, the counter using a negative age GK flip-flop, okay, as I've been mentioned to you, but it is still count up because the clock is connected to Q, okay. So this is the timing diagram of the 4-bit asynchronous binary counter. So in the example, the counter using a negative age, but it is still count up because it is connected to the Q, okay. So you see here, the counting sequence is still the same, where it will count at each clock pulse, okay, but this time the changes of the counter will occur at the negative age of each clock pulse. So you see here, for the first one we have, okay, so the Q3 is the MSB and Q0 is the LSB. So 0000, 0001, 0010, 0011, 0100, 0101, 0110, and so on, okay. And at the 15th, what you call a pulse of the clock, the output will become 1111, and at the 16th clock pulse, the output will reset back to 0000, okay. Next, I will show you different design of counters based on different types of flip-flop and types of functions. Okay, here we have the positive age triggered flip-flop categories and also the negative age flip-flop categories. And these are the functions that we want our counter to compute, whether it is count up or count down. So if you have a positive age trigger flip-flop, and if you want your counter to be count up, the input of the what you call the flip-flop 1 of the counter must be connected to the output Q bar of flip-flop 0. So the flip-flop 0 is directly connected to the clock, okay. But if you have the negative age triggered flip-flop where you have a bubble at the clock input, if you want your counter to be count up, you must connect your input clock of flip-flop 1 to the output Q of flip-flop 0. And if you have the positive age of flip-flop and you want your flip-flop to be count down, you must connect your input clock of flip-flop 1 to the output Q of flip-flop 0. And if you have a negative age triggered flip-flop, where you have a bubble at the clock input, so if you want your counter to be countdown, you need to connect the input clock of flip-flop 1 to the output of Q bar at flip-flop 0, where flip-flop 0 is the LSB because it is directly connected to the external clock. So from here, you can see that if we want to design our counter based on specific function, we need specific connection based on the type of our flip-flop, whether it is positive age or negative age. Okay, so you must know how to determine the circuit connection in order for you to create and design the correct counter circuit. Okay. So this is a summary of the asynchronous binary counter. So basically, the circuit connections for asynchronous counter is almost the same, where the external clock connected to the LSB. Okay, so actually the circuit connection for asynchronous counter is almost the same, where the bits number of the counter is depending on the number of flip-flop. So if you want to have an extra bits, you just need to connect an extra flip-flop to the counter. Okay, so the clock for each flip-flop comes from the previous flip-flop except for the first flip-flop, because the first flip-flop is connected to the external clock. So every flip-flop operates in toggle mode. Okay, so because we set the J and K input into 1, therefore it is operate in toggle mode, which is the next output is a complement of the previous output. If the previous output is 0, the next output is 1. If the next output is, if the previous output is 1, the next output will become 0. So if you want to operate in toggle mode for SR flip-flop, you need to set S to Q and R to Q bar. And for JK flip-flop, you must set JK input into 1. Both JK you must set into 1. And for D flip-flop, you must set the D input into Q bar. And for T flip-flop, you must set T to the value of 1. Therefore, all these functions and all these type of flip-flop can be used to generate a counter if you set this particular value as the input of each and every flip-flop. So the design connection is still the same. If you want more bits, just add more flip-flops. So as I've mentioned to you before. So the difference in connection will determine whether we want to count up or down, and by using which type of flip-flop, positive or negative age triggered. So as I have already shown you in the previous slides, so if we want to design count up or count down, so we need to define what is the type of flip-flop that we have, whether it is positive age triggered and negative age triggered, and then we can define the correct connection for the flip-flop to conduct several specific function. Okay, whether we want it to count up or count down. So next we'll move to the asynchronous decay counter. So previous lesson we learned about asynchronous binary counter, where we wanted to count 1 1 1 0, okay, 0 0 0 1 1 1 1 0. But this time we wanted to count the decay counter, which is from 0 to 9. So the modulus of a counter is defined as the number of unique states through which counter will sequence. So previously, the possible number of state, which is the maximum modulus of counter, is to the power of n. Okay, so modulus is actually the state. So counter can be designed to have number of state in their sequence that is less than 2n. So right now, you can know that if we have a total of 2n states, but actually we can design a counter that has a state which is less than 2n. Okay, so it means that our state doesn't necessarily become to the power of n. So this type of sequence is called a truncated sequence. Okay, So one common modulus for counters with truncated sequence is 10. That is called as decade counters. Okay. So this counter has sequence counts of 0000 through 91001, and it is referred as a BCD decade counter because the 10-state sequence is in BCD codes. So from the previous lesson, you already learned that the BCD codes has a total of 4 bits. And this type of decade counter count from 0, which is 0000. So you see here, it has a total of 4 bits through 91001, which is 4 bits. And therefore, it is referred as BCD decade counters. Okay, so to obtain a truncated sequence, it is necessarily to force the counter to cycle before going through all of its normal states. So because you see here, right now, we want it to count from 1 to 9. But according to the previous definition, the total number of states that the counter can have is to the power of n, where n is the number of flip-flops. So for a synchronous decade counter, it has a total of 4 flip-flops. So 2 to the power of 4 will become 16. But we just wanted to count until 9. So we don't need the 16 counts of the 4 bits of counter. So what we can do is we need to truncate the counter. So in order to truncate the counter, we need to force the counter to cycle before going through all of its normal states. Okay, for example, the BCD decade counter must recycle back to the state 0000 after state 0001. Okay, so for the BCD number, after the number of 1001, the next number will become 1010. So we don't want that counting. We just want the count to stop up until 1001. Okay. Note that the decade counter will require 4 flip-flops because the 3 flip-flops are insufficient, because 2 to the power of 3 will become 8. So it is not enough to create a decade counter because we need to have 9 different counting. Okay. So to achieve recycling after the count of 9, which is 1001, the counter has to decode 10. Okay, the value that we doesn't have. Okay, it's not the value that we didn't want. Okay, which is 1010 with a NAND gate, and connect the output of the NAND gate to the clear, so the CLR inputs of all the flip-flops. Okay, so in order for us to truncate the counter, we need to decode the counter. So to decode the counter, we need to use NAND gate. Okay, so this is the circuit of the asynchronous decade counter, where we have a total of 4 flip-flop, FF0, FF1, FF2, and FF3, and some of the output of flip-flop, which is from flip-flop 1 and also flip-flop 3, is connected to a NAND gate, and the output of NAND gate is connected to each input of CLR. Okay, so at the beginning of this lesson, I already show you what is the function of the CLR. So the function of CLR is to clear the counter. Okay, so it will make the counter to become 0000. So you see here, so we want to clear up the counter when the state of the output from flip-flop is 1010. So right now we will observe what will happen if the value of the counter is 1010. Okay, so FF3 is the MSB and FF0 is the LSB. So when the output of the counter is 1010, so the pins which is being connected to the NAND gate, which is pin from Q3 and also Q1, will be connected to the NAND gate. So 1, 1, so 1 multiplied by 1 equals to 1, and then we complement because it is NAND gate, so we will get the output of 0. So the output of 0 will travel to each CLR pin which is connected to each flip-flop. Okay, so when 0000 is being given to each flip-flop, so you see here it is active low enable, so it means that the next state of the flip-flop will become 0000 and it will be reset. Okay, so this is where the decoding takes place. So we have to add one NAND gate in order to make sure that after it counting 1001, the counter will be reset. Okay, so notice that only Q1 and Q3 are connected to the NAND gate inputs. So this arrangement is an example of partial decoding, in which two unique state Q1 equals to 1 and Q3 equals to 1 are enough to decode the count of 10. Okay, so this is because none of other states 0 through 9 have Q1 and Q3 high at the same time. So because of that, because of Q1 and Q3 has one unique state, so we can connect Q1 and Q3 to the NAND gate. So consequently, when the counter goes into the count 10 1010, the decoding gate's output goes low and asynchronously resets all of the flip-flop. So when the count reach 1010, so it will activate the reset pin and the counter will be automatically become 0000 because of the partial decoding that we have done. Okay, this is the binary state sequence for asynchronous decay counter. So you see here we have this is the initial state 1 2 3 4 5 6 1 2 3 4 5 6 7 8 and also 9. So we have 9 states, and these states are not present in asynchronous decay counter because at this state the counter will be reset back to 0. Okay, this is the timing diagram for asynchronous decay counter. So based on this timing diagram, notice that there is a glitch in Q1 and CLR bar. So here there is a glitch at Q1 and also CLR bar. So why does this glitch happen? So the reason of this glitch is that Q1 must first go high before the count of 10 can be decoded. So several nanoseconds after the decoding gate goes low. Okay, so from the previous explanation, I already told you that for asynchronous decay counter, the counter can be count until number 9, and after number 9 it will be reset to 0 back. Okay, so in order for us to reset at 0 after the count of 9, we need to do a partial decoding by adding NAND gate to the counter. Okay, so what is actually happening at the output of the flip-flops? So how does it reset the output of 0 after the count of 9? So you see here, if as initial, the initial state of the counter is 0000 because we wanted to count from 0. Okay, and then it will go through the normal counting state until it reach the number of 1001, which represent number 9. Okay, so at the 10th pulse of the clock, okay, at the falling edge, because this is actually the negative age triggered counter, so at the 10th clock pulse, the output of Q0 will toggle because Q0 is directly connected to the clock signal, so it will go from 1 to 0. And then at the same time, Q1 will also toggle because the output of Q0 bar in this situation will change from 0 to 1. Okay, so it will change the output of 0 of Q1 to output of 1. So when the asynchronous decay counter detects that the number of 1010, so it means that the number of 10 is created. So when the number of 10 is created, the output of Q1 and Q3, which is directly connected to the NAND gate, so 1 multiplied by 1 will become 0, so it will produce 0 to the CLR bar. So the CLR bar pin will be activated for all the flip-flop, and it will make the final output, it will make the next output of the flip-flop to become 0, 0, 0, 0. So this is how the glitch is happening, because the the output of Q1 and the output of the input of CLR bar is changing momentarily only before it goes to reset state, because the reset state will interfere whatever output is happening and whatever output that we have at the flip-flop. Okay, so next is the advantage and disadvantage of a synchronous counter. So what are the advantage and disadvantage? So the advantage of a synchronous counter is it is easy to design because it is simple. And the disadvantage of the asynchronous counter is the propagated delay will accumulate, as in ripple binary adder, which may cause a missing counting state, especially at the high frequency operation. So as I've been mentioned to you in the previous lesson, a flip-flop will have a propagation delay inside the logic gate. So in the counter, the propagation delay will be accumulated based on the number of flip-flop or bits that you are using. So in this disadvantage section, I will show you two different samples. Okay, so the first case is operating at low frequency of 1 megahertz. So this is the low frequency state. Okay, so for each stage, let's say there are 50 nanosecond delay, and it accumulates up to 150 nanosecond at the third stage. Okay, so you see here we have 3 bits of counter. We have A, B, and C. So at each stage, we have 50 nanosecond delay. Okay, so let's say the period of the clock frequency is 1000 nanoseconds, and then we convert it, we will get 1 megahertz. Okay, and then let's say at the first stage of output, we have 50 nanosecond delay. So at the second stage of output, which is B, we have 100 nanosecond delay, and then the output C, we have a total of 150 nanosecond delay. So you see here, the accumulated delay is still lower than the period of the signal, which is 1000 nanoseconds. Therefore, there is no effect to the counting sequence. So first, you see here, for the asynchronous counter, if we have a delay for the first stage, so the second stage will accumulate. Okay, so for example, if we have 50, the second stage will become 100. So the third stage will become 150. So if we have the fourth stage, so the fourth stage delay will become 200, and then it will become 250, and so on. So you see here, the accumulated delay, because this example we only have 3 stages, so the accumulated delay is only 150 nanosecond. So it is still lower than the period of the clock. Okay, so there are no effect to the counting sequence. So when we simulate the counting sequence, you will still have all of the sequences that you want, 000 until 101 for this example. Okay, what if the frequency is high? So what will happen to the asynchronous counter? So this is the second case where the counter is operating at higher frequency of 10 megahertz. So the clock period is only 100 nanoseconds because we have a higher frequency. So the clock period must be reduced. So for a 3-stage flip-flop, the accumulated delay is the same as before, which is 150 nanosecond. But the current accumulated delay is more than the clock period, because for this case, the clock period is 100 nanoseconds. But the accumulated delay for a total of 3-stage flip-flop is equals to 150 nanosecond. So it is greater than the clock period. Therefore, there is a missing count. So in this stage, the example of a count of 100 does not exist. Okay, so let's see. So we have a period of 100 nanoseconds, and then as usual, as the previous example, let's say we have a delay of 50 nanosecond for the first stage, and then it accumulates to hundreds nanosecond in the second stage, and then it accumulates to 150 nanosecond for the third stage of the output. Okay, so you see here, when we starting the count of the counter, so as usual, the initial state is 000, and the next stage is 001 because C is the MSB, A is the LSB. And then at the next counting, it is 010, so it's still counting correctly. But the next count is 011, so it is still counting correctly. But at the next counting, it is directly counting to 101. So where is 100? Because the next count of 011 is 100. But right now, the 100 is missing from the count. So the 100 condition does not occur in this asynchronous counter if we set the operating state of 10 megahertz. So as the conclusion, if you are using an asynchronous counter, you must not use a higher clock frequency because it may have some missing count inside the counter. So you must use a clock signal which is lower frequency so that you will not missing any count inside the asynchronous counter. Okay, so that's how you wanted to overcome the disadvantage of the counter. Okay, next we will go to the next type of counter, which is synchronous counter. So what is actually synchronous counter and how it works? So let's continue. Synchronous counter is one in which all flip-flops in the counter are clocked at the same time by a common clock pulse. So this is the circuit diagram for synchronous counter. So as you can see here, the synchronous counter, the input clock inside each flip-flop is being connected to the external clock. So it means that the state of each flip-flop inside synchronous counter will change its state with each clock pulses. So this is the major difference between synchronous and asynchronous counter. So next we proceed with the asynchronous counter IC, which is 74X293. So 74X293 is an asynchronous counter IC that has 4 JK flip-flops with output of Q3, Q2, Q1 and Q0. So this IC has a total of 4 flip-flops with 4 bits of output. So 2 flip-flops have their own CP, which is external clock pass input. So clock input to FF1 and FF0 labeled as CP1 bar and CP0 bar, while FF2 and FF3 comes from the output Q1 and Q2 respectively. So the first flip-flop has their own external clock pulses input, but the later 2 flip-flop, the input of a clock will be directly connected to the previous output Q. So each flip-flop has CD input to reset that are connected to 2 input NAND gate from MR1 and MR2. So IC reset when MR1 and MR2 is high. Okay, so in order for you to get a clearer perspective of this IC, so I will show you the circuit diagram. So this is the circuit diagram of 74X293 IC with a total of 4 different flip-flops. Okay, so for the first 2 flip-flop, it has its own clock, what I call external clock input, which is CP0, which is connected to FF0, and CP1, which is connected to FF1. Okay, so for to reset the counter, we need to give the input to the MR1 and MR2. So if we wanted to reset the counting, we need to give the input of 1 for each MR1 and MR2. Because if we give input 1 for MR1 and MR2, 1 multiplied by 1 equals to 1, and then will be complemented by the NAND gate. So each input of CD will get 0. So when input CD gets 0, it will be activated the reset function, and the counter will be reset. And for this counter, it has a total of 4 bits of output. Okay, so in terms of outputs, the MSB part of the output is Q3 and the LSB part of the output is Q0. So usually it will be in Q3, Q2, Q1 and Q0. Okay, so all of this circuit will embedded inside the 74X293 asynchronous counter. So you can see here, this is the pin assignment 8, 4, 5, 9, 10, 11, 12 and 13. So this is the input of what they call external clock for each what they call the first 2 flip-flop, and this is the reset. Okay, this is the reset input MR1 and MR2, and this is the output. Now I will show you the example question given for asynchronous counter IC. So in this example, show how the 74X293 is connected to become a mode 16 counter. So in the previous slide, I already showed you what is the definition of modulus inside a counter. So modulus is defined as the number of state inside a counter. For example, if you wanted to count from number 0 to number 9, you need to have a total of 10 state. So it means that you need mode 10 counter, because number 0 until number 9 needs a total of 10 state. 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So those each numbers represent each state. Okay, so in order for us to validate whether one 74X293 IC is valid to become a mode 16 counter, so you need to substitute inside the equation of maximum number of state. So in order for us to calculate the maximum number of state, you are using the equation of 2 to the power of n, where n represent the number of flip-flops. So as 74X293 IC has a total of 4 flip-flops, so 2 to the power of 4 will be equals to 16 state. So this IC is valid to become a mode 16 counter, because mode represent states. Okay, so since mode 16 required 4 flip-flops, so all flip-flops in 74X293 are used. Therefore, Q is connected to CP1 while CP0 is connected to external clock. So this is the answer to the question where you have the 74X293 IC. So first, what we need to do if we wanted to design a mode 16 counter, first we need to connect MR1 and MR2 to the ground, because we doesn't want to reset the counter at any state while it is counting. Okay, so what about the input clock? So for input clock, an external clock is connected directly to the CP0, the first flip-flop. So the first flip-flop become the LSB part of the counter. So Q0 become the LSB part of the counter. And then the output of the first flip-flop will be connected to the input clock of second counter. So this is what you can say here is that this example show you how to create a 4-bit asynchronous counter by using 74X293, because it has 2 input for external clock signals. But for asynchronous counter, we need to have only 1 clock signal. Okay, 1 external clock which is connected to the input clock. So the other input clock will be connected to the previous flip-flop. Okay, so next example, you need to show how the 74X293 is connected to become a mode 10 counter. So this time, this example wanted you to design the mode 10 counter. So previous slide show you how to design mode 16 counter, but how to design a mode 10 counter? So first, we need to check whether one number of 74x293 IC is enough to create a mode 10 counter. So since 2 to the power of 4 is equals to 16 and it is greater than 10, which is mode 10, so the states inside the 74x293 is enough to create a mode 10 counter. So the solution is, since mode 10 required 4 flip-flops, so all flip-flops in 74x293 IC are used. So therefore, Q0 is connected to CP1 while CP0 is connected to external clock. So meanwhile, since the counter count from 0000 to 1001, which is number 9, so the counter must be cleared 0000 when reached to 1010. Thus, Q3 and Q1 are connected to MR2 and MR1 respectively. So basically, a mode 10 counter is equals to the decade counter, where we wanted to count from 0 until 9. Okay? So when we wanted to count from 0 until 9, we need to have 10 different states. Okay? So when the counter are counting from 0000 to 1001, so it is still valid for mode 10 counter. But when it goes to the next counting where it counts 1010, so the counter need to be cleared. Why? So this is because if the counter is not cleared, the counter will become mode 11 counter. So we doesn't want the 11 number. We only want the mode 10 counter. We only want 10 states. Okay? What you can do is that, as usual, you need to connect the external clock to the CP0. Okay? And then you need to connect the what we call the Q0 output to the second clock signal, because you wanted to provide a conventional type of 4 bits asynchronous counter. And then, as you see here, if the counting reach a number of 1010, it need to be reset. So inside this IC, where is the reset input? So the reset input is MR1 and MR2. So in order for you to activate the reset function, you need to give MR1 and MR2 each 2 input of 1. So at 1010, the counter need to be reset. So in this situation, we have 2 output of 1. So each output of 1 will be connected to each input of MR1. So that 1 will be connected to MR2 and 1 will be connected to MR1, and it will reset the counter when it reaches the count of 1010. Alright? So next is show how the 74x293 IC is connected to become a mode 50 counter. So how we wanted to design a mode 50 counter? So counter that has a total of 50 states. So as usual, we need to check whether one IC of 74x293 is enough to design the mode 50 counter. So as usual, we substitute the equations. So 2 to the power of 4, because it has 4 flip-flop inside the 74x293. So it is actually less than the required number of states, which is required by the question. So what we can do is that we need to use another 74x293 IC. Okay? So the solution is, since mode 50 required 2 74x293s that are cascaded together. So the first counter as function mode 10, and the output is fed up to the CP0 at second counter, which function as mode 5. Okay? So in order for you to get a clearer answer, let me show you the answer first. So this is the first 74x293 IC, which is being used as a mode 10 counter. And this is the second IC of 74x293, which is being used for mode 5 counter. So in order for you to verify how we wanted to design the mode 50 counter, you need to use 2 counters. So the first counter, it is used as mode 10, and the second counter, it is used as mode 5. So 10 multiplied by 5 will become mode 50. So now, the connection of designing the mode 10 counter has been shown in the previous slide, where you have one external clock, and then output of Q0 will be connected to the second input clock, and then at 1010 the output will be reset, so MR1 and MR2 need to be set to 1. So Q3 and Q1 will be directly connected to MR1 and MR2. So this is the connection for mode 10 counter. So what about mode 5? So for mode 5 counter, first add the count of 0, 1, 0, 1, which is the number of 5. Okay, because mode 5 counter has 5 states. So it needs to count from 0, 1, 2, 3, and 4. Okay, so at number 5, which is equals to 0, 1, 0, 1, so the counter will reset. So can you guess how to connect to become mode 5? So in order for us to reset the counter to become 0, so we need to connect MR1 and MR2 to the input of 1. So in this example, we have two output of 1, so you can just connect directly to each and every MR1. Okay, so as usual, Q0 will be connected to the CP1 because we want to have the conventional 4 bits of asynchronous counter. So in the solution, it is mentioned that the two 74X293 IC are cascaded together. So which input will what is the input of the CP0? So if you wanted to connect to 74X293 IC altogether to become a total of mode 50 counter, so the input of CP0 must be connected to the LSB part of the output that comes from the previous counter, which is mode 10. So in mode 10, in this counter, the MSB part of the output is Q3. So Q3 will be directly connected to the input clock of CP0. So this is how you can design the mode 50 counter by using two different 74X293 IC. Okay, because the first IC acts as mode 10 and the second IC functions as mode 5. So 10 multiplied by 5 equals to 50. Alright. So next is the synchronous counter IC. So for synchronous counter IC, 74X163 is a popular synchronous counter IC. So it can be initialized by starting value by giving a low pulse at the PE input and any required starting value at P3, P2, P1, and P0. So for synchronous counter IC, you can start counting at any number by enabling the PE input and also put your initial counting value P3, P2, P1, and P0. So to enable counting, both CEP and CET input must be high. Okay, so in order for you to enable the counter to count something, so you need to enable CEP and CET input. So the input SR synchronous reset only valid at the positive trigger age, and the output TC terminal count becomes high when counter reach 1111. That is useful to enable other counters in cascade configuration. Okay, so previously you see that for a synchronous counter IC, in order for you to cascade the IC, you need to connect to the first, for example, we have one asynchronous counter IC and the second asynchronous counter IC. So in order for us to cascade it together, the MSB output of the first counter must be connected to the first input clock. Okay, first input clock of the second second counter IC. So for synchronous counter, this is the logic symbol for 74X293 asynchronous counter. So first we have the counting starting value. So as I've mentioned before, you can customize your synchronous counter to count starting from your own customized value. So if you wanted to get your counter to start from your custom value, you need to give the input of 2, P3, P2, P1, and P0. And in order for you to enable the counting starting value, you need to give 0 to the input PE. Okay, And then the input synchronous reset is you wanted to reset your counter. And the input of CEP and CET, it is the input which is you wanted to enable the counting. So if you didn't give any input to CEP and CET, your counter will not be started. So it will not start counting. So as usual, CP is the clock input. And you have a total of 4 outputs, which is Q3, Q2, Q1, and Q0, where Q3 is the MSB and Q0 is the LSB. And lastly, you have the output terminal. Okay, so this is the terminal count. Okay, so when the output become 1111, it means that it has finished counting. So what if we wanted to cascade the counter of synchronous counter IC, you need to connect TC to another synchronous counter IC. So later on I will show you some example. Okay, so this is the first example of synchronous counter IC. So show how the 74x163 is connected to implement a mode 13 counter. So as you can observe from the amount of bits at the output of this IC, it means that it has a total of 4 different flip-flops because it has 4 outputs. So as usual, we need to calculate the number of states, okay, because mode 13 represents state 13. So this question is going to be used only one 74x163 IC because the number of state inside this IC is greater than the required inside the question. So the solution is the mode 13 counts from 0 to 12. So since counter clear synchronously after a clock pulse arrive, in order to detect number 12, only need to detect high value at Q3 and Q2 to NAND gate, which will be activated when count reaches 1100. So you see, this is the answer for this question. So first, you see here, P3, P2, P1, and P0 is not being connected to any input because we doesn't have our count. We doesn't want our counter to start from any custom value. Okay. So next, we see here, PE and CEP and CET all are connected with input 1. So because we doesn't want to activate PE because we doesn't want our counter to start counting at customized value, and CEP and CET is connected to 1 because we want our counter to start counting. And then as you see here, the requirement of counter is mode 13, so it need to count from 0 to 12. Okay, so after it reached the value of 1100, okay, when it reached the value of 1100, the counter need to be reset. So how to reset the synchronous counter? So in order for us to reset the synchronous counter, you need to give the input 0 to the SR. Okay, so in order to give the the input of 0, so you need to observe what is happening at the output. Okay, so at the output at 1100, the counter need to be reset. So at each value of Q3 and Q2, when Q3 and Q2 both are equals to 1 and Q1 and Q0 both are equals to 0, it needs to be reset. So Q3 and Q2 both will be connected to the NAND gate so that the output of NAND gate will produce an output of 0 and it will be given to the SR. So at 1100, the counter will be reset counting and it will start again counting from 0 to 12. Okay, because 1100 is equals to the number of 13. So we doesn't want the number of 13 inside our counter because it only counts from 0 to 12. Alright. So next, show how 74x163 is connected to make it count from 2 to 8. So now, you see here, the asynchronous counter question, it asks you to count from a customized value. So it doesn't count starting from 0, but it wants you to start counting from the number of 2. So can you guess how many states it requires? So in order for you to determine what is the number of state, you can just count the value of the states that has been given. So right now they want you to count from 2 to 8. Okay, so right now we will count together: 2, 3, 4, 5, 6, 7, 8. So from this counting, you can say that it has a total of 7 states. Okay, so as usual, we need to substitute inside the number of state because we wanted to determine what is the number of IC required to design the counter that counts from 2 to 8. So our state that we are calculated previously, we have a total of 7 state from 2 to 8. So it is less than the maximum number of state for 74x163. So we can just use 174x163 IC. Okay, so the solution is to make counting from 2, which is 0010, to 8, which is 1000, the counter must stop counting at 8 and starting counting from 2. So to do that, the detection of logic 1 at Q3 is enough to make the counter stop at 8. So connect the Q3 at PE with 0010 as parallel input. Okay, so this is the answer for this question. So this time, the counter wants you to count from 2 to 8. So what you need to do is you need to connect the input to the P3, P2, P1 and P0. So you need to connect 0010 because P3 is the MSB and P0 is the LSB. So 0010 represent the number of 2. And then the next thing that you need to do is you need to enable the PE, which is the counting that starts from this value. Okay, so as usual, you doesn't want to manually reset your your counter, so you need to disable the SR and you need to enable the CEP and CET because you want your counter to start counting. So as usual, you need to connect your external input clock. Okay, so this time what the counter wanted you to do is that after it counts the number of 8, it will reset. Okay, so in order for us to reset the counting of what we call a customized value of counter starting count, so you need to connect the output that has the the finish counting. So this time the counter will finish counting at the output will be at the output of 1000. So after this state, the counter will be reset. So what you can see here is that at this state, you need to give the PE input the input of 0. Okay, so you need to activate the PE in order for you to start counting from this value. Okay, so what you need to do is you need, when this value is achieved, so this value is equals to 1000. So 1 will be connected to the NOT gate, so it will become 0. So 0 will be connected to the PE. Okay, so PE will be activated and the counter will start to count from this value 2. Okay, until it reaches the number of 8, which is 1000, and then it will go back and activate again the counting sequence of 2. Okay, so it will rotate again and rotate again. All right, so next is the next example is show how 74x163 are connected to become a mode 256 counter. So right now we need to have a total of 256 different states. So as usual, we need to substitute the maximum number of state of 74x163. So right now the maximum number of 174x163 is less than the total number of state required by the question. So what you need to do is you need to add another counter. Alright, so since mode 256 required two 74x163s that are cascaded together, so the left device is LSB counter while the right is MSB counter. So both counter must be enabled, thus PE and SR are high. So the left counter count continuously, so that's why CEP and CET is fixed at 1. So the right counter only start counting when the left counter overflow, CEP and CET connected to TC. Okay, so this is the answer of this question where we wanted to design a mode 256 counter. Okay, so in this question, it doesn't mention what is the custom value of starting point of counting. So generally, you doesn't have to put any input at P3, P2, P1, and P0. Okay, so next, at the LSB counter, so which is mode 16. So in order for us to operate as a mode 16, what you need to do is you need to disable the PE input, because we doesn't want the counter to start from any custom input, and then we doesn't want to reset our counter, so we disable the input SR by giving the input of 1. And then we wanted our counter to start counting, so we need to give the input of 1 for CEP and CET. Okay, and as usual, we need to give the external input clock to each synchronous counter. So for this IC, if you wanted to design a cascaded connection, what you need to do is you need to connect the TC pin. So as I've been previously mentioned, so the function of TC pin is that when the output of the the output of 74x163 become 1 1 1 1, with which indicates that it already have reached the maximum number of states, so TC will be activated. So TC will become 1, and it will enable the second counter to be operated. Okay, so for the second counter, when the LSB counter has reached its maximum state, so it will activate the TC. So TC will activate the second counter, and the second counter will start counting. Okay, so as usual, we need to disable the PE and SR because we doesn't want to reset our counter, and we doesn't want our counter to start from the custom value. Okay, so from previous example where I show you how to design the asynchronous counter with cascaded connection of 50, mode 50, we combine together mode 10 and also mode 5 counter. So it will become 10 multiplied by 5, become 50. But this time, we wanted to design a mode 256 counter. So we need one LSB counter, which is mode 16, and one MSB counter, which is also mode 16. So 16 multiplied by 16, it will become 256. So this is how you wanted to design the mode 256 counter inside the counter IC. Okay, so I hope that you will understand on how you wanted to design the counter and how you can implement the counter design inside your electrical digital circuit. Alright, so that's all for today. Thank you.